Record. All right, so, oops. Welcome back. Happy to have Alice Lim from Harvard, who will give background on p-adic theory.
Thanks. Yes, so today we'll be talking about the second background talk for Sasha's lectures, and this will be covering the basics of p-adic Hodge theory. So first I'll define C, or also called CP, and what Tate twists of it are. And then I'll state the Hodge-Tate decomposition, which gives an analog of Hodge decomposition for étale cohomology, and then compute one of the embeddings using an abelian variety. And then analogously, like there's a comparison between singular cohomology and de Rham cohomology, there's also a comparison theorem between étale cohomology and de Rham cohomology, and I'll state the theorem for that. And both of these comparison isomorphisms will use something called period rings. The de Rham comparison one will use this B de Rham period ring, and the last section will be just constructing this period ring. Here are references that I use, so I just won't reference these during the talk, but these are what I use to prepare the talk. Okay, so I'll get started. K for this talk will be a complete, discretely valued field of characteristic 0 with a characteristic P perfect residue field. And then I'm going to define what I'll call C for shorthand to be also what sometimes people call CP, and that is the algebraic closure, an algebraic closure of K, which you then complete with respect to an absolute value on K bar. This is just like the p-adic completion of K bar. So this C is algebraically closed. And also by continuity of having a Galois action on K bar, we also get a Galois action on C, which preserves absolute value. GK, which is going to be the Galois group of K bar over K, acts on C and preserves the absolute value. Okay. So now I'll define the Tate twists. So the first Tate twist, CP1, is going to be the inverse limit of the mu p ends with the Galois action on them. And so this is like thinking about mu p and then mu p squared, with the transition maps being exponentiating by p. And if you chose a compatible choice of roots of unity, we can identify it with ZP. We would get an identification with Z mod P squared, and dot, dot, dot. So this would give us just the inverse limit of Z mod P to N, and then this is Z. This is multiplication. Or sorry, this is not P. Okay, so the p-adic cyclotomic character is this character chi from GK to ZP cross, is defined so that for all n and all sigma in GK, we have that sigma acts on a root of unity by sending it to the exponent zeta p to the n to chi of sigma. And you can check that this is actually how the Galois action acts on roots of unity in a compatible way. And so using this identification above, we see that ZP1 is just ZP with the Galois action of chi, the p-adics of the atomic character. And then analogously, we can define the rth Tate twist as just being the tensor, rth tensor power of the ZP twisted by 1. ZP twisted by 1, tensor by r for r greater than or equal to 0. And then for negative twists, that's just taking the dual of the rth Tate twist. And also, if you had a representation of GK, you can also define the Tate twist of M just by tensoring with ZP twisted by R. And so this is like the same underlying, the same underlying I just tensored. Okay, so yeah, it is. So it's the same underlying module structure, but just with a modified GK action. So for example, we can define the Tate twist of C, which has the Galois action listed by R. And the Galois action, you can just think of as like sigma acting on M is just going to be chi of sigma to the R times the old sigma acting on M. Okay, so now I've defined the Tate twist of C, and if you have a profinite group acting continuously on a abelian group, you might ask about its continuous group cohomology. Do you have a question?
Oh, no, sorry.
And so Tate answered this question in his paper on p-divisible groups. The Galois invariants of C itself are just the original p-adic field K, so you don't introduce any transcendental invariance when you take the completion. And the H1 is of GK acting on C is a one-dimensional vector space over K. And then also we can say that the H0 of GK acting on the Tate twists, the fixed points of the GK action on the Tate twist is just 0, so there are no fixed points. And then the H1 of the Tate twist is also 0. So I won't really explain in detail how they prove this, or how Tate proves this, but the idea is that he sort of splits the proof into two parts, where he takes some ZP extension, which is totally ramified, called K infinity over K, and then also considers K bar over K infinity and takes the completion of both of those, which is C and K infinity completion. And then both of these have an action by different Galois groups. This has the action by the Galois group of K bar over K infinity, and then this has the action of the Galois group of K infinity over K. And then so separately, he computes the Galois cohomology of these two different Galois actions and then fits them together using a Hodge-Schultz-Serre spectral sequence to talk about the Galois cohomology of this whole Galois group by studying the two different pieces.
Sorry, what did you guys?
Sorry? Oh, vector space.
Was there a condition on R too?
Oh, R is non-zero. Yes, good catch. Oh, and right, this is also doing some detailed study of trace maps in these fields. Okay. So I also wanted to mention that the H1 continuous Galois cohomology will classify extensions of this one-dimensional representation by the trivial one-dimensional representation, and this cohomology group being 0 tells you that there are no non-split such extensions. However, there are non-split extensions if you replace C with K bar. So I guess in a way this theorem is saying that once you go up to C complete and you're talking about C representations, the representation is somehow better behaved. So now we'll move on to section 2, which is the Hodge-Tate decomposition. And first, I want to say something about what is p-adic Hodge theory really about. So p-adic Hodge theory is motivated by studying the Galois representations that show up in the tall cohomology of smooth proper varieties. So this is motivated by studying the tall cohomology of x phase change to k bar with qp coefficients. And since the Galois group acts on this xk bar, you have an action of the Galois group on the cohomology as well. And the one question that's important is that what can these Galois representations recover about the geometry of X? So to build up the analogy, I want to say that if you had a smooth proper scheme over C, you have a classical Hodge decomposition, which you won't mention, where you can decompose the singular cohomology of the C points of Y with few coefficients, but actually you have to base change up to C in terms of these other cohomology groups using the sheaf of differentials, the direct sum of the H n minus j y omega y j. And so in the same paper on p-divisible groups, Tate showed that there is an analogous decomposition for H1 et al. Of an abelian variety over a p-adic field K with good reduction. And he also conjectured that such a decomposition would exist in general beyond just abelian varieties. And this does turn out to be the case, and that is what the Hodge-Tate decomposition is. Oh, yeah, it's over a field, so yeah. Let's see through it. Sorry?
There's also canonical decomposition for
Oh,
Oh,
not one together.
still is. Right.
right. So, yes, stating the Hodge-Tate decomposition. Decomposition by Halting's 8. So if we have X a smooth proper K scheme and an n greater than or equal to 0, then we can have some decomposition of the Étale cohomology of X phase change to K with QP coefficients. And you have to base change to a bigger ring this direct sum over J and Z of the Tate twists of C. And then if you then take the Galois fixed part, so this is a tensor product of Galois representations, you can take the Galois fixed part, and that will be isomorphic to the right-hand side of our original classical Hodge decomposition. Hn minus j x omega x over k j, but now algebraically defined, so I'm using like a sheaf of differentials here. So this is an isomorphism as graded k vector spaces. And so it's sort of like how we didn't get a Hodge decomposition in the classical situation until you extended scalars and you base change to this larger ring C. So analogously here, we don't get a Hodge decomposition until we base change to this larger ring. And this larger ring is our first example of a period ring. So the ring EHT, which is this big direct sum of C twisted by J, is called the Hodge-Tate period ring. And also I want you to observe that the theorem tells you that the Hn et al. Galois representation recovers the Hodge numbers.
So the CJ does not have anything to do with K.
Sorry. Sorry.
The CJ thing doesn't have anything to do with K.
Well, it has a Galois GK action on it.
CJ.
Yes.
The big C is.
So it does keep track of like the K through the Galois action.
K was a tiny fish.
It's
Just
still,
for no,
the K is still like
Yeah, I'm fixing K as like some
the
concrete discrete value here over QP. Okay. Yes. Right, so this is the Hodge-Tate decomposition, and I wanted to give some example of how to understand this in the case of abelian varieties. So the theorem plus a little bit of extra work called the Serre-Tate lemma tells you that you can rewrite the theorem as Hn et al. Xk bar Qp base changed up to C should be isomorphic to this direct sum of the Hn minus Q x omega Q x over K tensored with C twisted by minus Q. It's just some rearranging of the previous theorem. And in particular, if we let x equals to abelian variety A and n equal to 1, then we get this decomposition of the et al. Cohomology of an abelian variety is isomorphic to the direct sum of, well, the only things that show up are when Q is 0 and when Q is 1. So we have H1A OA tensor with C, direct sum with H0A omega 1A over K, tensor over K, with C twisted by minus 1. And so we can actually construct the map which sends this piece into the et al. Cohomology, which I'll call alpha. This map is alpha sub A, and this is a Galois equivariant map. There are questions? Right, so this is our next part of the talk. now we're constructing alpha sub A. Suppose that, well, we're going to need that A has good reduction so that it extends to an abelian scheme A over OK. And let me just introduce a piece of terminology. O sub C is just going to be the valuation ring of C with respect to the absolute value, or you could think of it as the p-adic completion of the ring of integers of OK bar. All right, so to define this alpha sub A map, I'm going to consider this tower built out of many copies of the same abelian variety base changed to OC. And all of the transition maps are just going to be multiplication by P on the abelian variety. And so this is like this infinite tower. And if I take the limits of this, this is an inverse, maybe filtered limit of affine morphisms between schemes. So this limit really exists as a scheme, and which we'll call A infinity. This is an OC scheme, and it's a limit of affine morphisms. Okay, and I'm going to define the map pi to be just the projection map that naturally exists from the limit to like the first coordinate. Okay, so pi be as above. For morphisms of schemes, you get like a map in the other direction on sheaf cohomology. So we're going to get that this will induce a map on the sheaf cohomology R gamma A naught O A naught to, well actually A naught is just A, so A base change to OC, to the sheaf cohomology of A infinity. Okay. So the next step is to observe that by the construction of this inverse limit, well, you see that each A p to the n C points acts on A n in this inverse limit just by translating all the points by a torsion point. And this works, this action is compatible with transition maps. If we multiply by P on both of these things, this will be compatible with these transition maps. And then this tells us then that the inverse limit of the P torsion points will then act on the inverse limit of the ANs. So we get an action of the inverse limit of the A P to the N's, which is TP of A, the Tate module of A, acts on A infinity. Okay. And also observe that all of these TP of A things, they don't act on the first thing because all the torsion gets killed once you get to A0. So this map pi from A infinity to A0 is TP of A equivariant with the trivial action on A0. Okay, so I think one important thing I wanted to point out is to observe that we needed to be over, at least over OK bar, if not over OC, in order to define the TP of A action. on A infinity because we had to be able to translate by p to the n torsion points for arbitrarily large n. So that means you had to like pass to a very large extension. So to get this action as actual morphisms of schemes, we needed to base change. So
Are those eyes?
yeah, they're eyeballs. Okay, so now, oh yes, sorry, because this is a TP of A equivariant map, you can imagine that the image of the A0 cohomology inside the A infinity cohomology lands in the TP of A invariance of this A infinity cohomology. So there is a natural map going from R gamma A OC O AOC to, oh, I have not left myself enough space, to R gamma of a continuous group cohomology of TP of A acting on the sheaf cohomology, A infinity, O A infinity, oh sorry. There's a natural map from, because, sorry, I got ahead of myself. So TP of A acts trivially on A0, and so there is a map, it also acts trivially on the sheaf cohomology, and so there will be a natural map from something with trivial TP of A action to the continuous group cohomology of TP of A acting on R gamma of AOC. And then there is another map, just by functoriality, taking the TP of A cohomology, group cohomology of both the sheaf cohomology in A0 and the sheaf cohomology of A infinity. So this is just TP of A group cohomology of R gamma A infinity O A infinity. This is functoriality. Okay. Any questions so far? And the next step is that we want to, well, ultimately, what do we want? We want to map from sheaf cohomology to étale cohomology. So we have to like process this group cohomology to étale cohomology somehow. And one simplification is this fact that I'm about to state. The natural map, which sends OC to R gamma A infinity O A infinity, which is given by just OC being the constant sections of this scheme over OC, gives an isomorphism of complexes after taking p-adic completions. You can see Bot's notes for more details on how this is done, but it's not a difficult lemma to show. But that means that if we took p-adic completions of this map, we can then replace this complicated sheaf cohomology of this limit with something much simpler. Namely, we can replace this with OC after p-adically completing. So what does that become? This becomes R gamma A of C mapping to R gamma continuous of TP of A. Now it's just OC instead of the sheaf cohomology. And since we've P completed, this is actually the same as R gamma continuous of just the pi1 étale cohomology of A, because this is sort of the pi1 étale cohomology of an abelian variety is just the product of all the different Tate modules for different primes P, but we're talking about sort of like the p-adic part of it. So this will be continuous group cohomology for pi1 of A, but I think as maybe Gleb talked about, there will be then a map just to étale cohomology of A itself with the OC coefficients. And this is given by the map on sites. Well, if this is confusing, it's not important, but it's just given by the map of sites from the étale site to the finite étale site, which will change group cohomology into étale cohomology. And then we're basically done. In order to get this map, all we have to do is now take the H1 of both sides of the map, and we have to tensor by C. So this becomes now H1 AOC C, tensor by C maps to H1 étale AC with QP coefficients, tensor with C QP coefficients. And so this gives us exactly the alpha sub A that we wanted. Are there any questions? Yes?
How do you get this identification right of continuous cohomology with étale versus the continuous action of the pi1 étale?
So this is because if you the finite étale site, if you use the finite étale site to define cohomology, you would get this cohomology. And if you used the usual étale site to define cohomology, you would get this cohomology. And if you have a map of sites, you also get a map going the other way of the cohomologies of those sites.
I was actually wondering about the equality above that.
Oh, I see. This one I'm a little bit fuzzier on, but because the pi1 étale of A is the product of P L of A's for all L prime, and I guess because I took a P completion here, I kind of only care about sort of these have to be continuous actions. So this, I probably can only take the p-adic part, the pro-p part of the pi1 étale, which is why I then reduced to this equality.
I guess it's Comanche's theorem.
Sorry?
I guess it's Comanche's theorem, right? Representations of
Yeah.
coality
Oh,
prime to L flavors.
yes. Good. Now that we have defined this example of one part of the Hodge-Tate decomposition, let's move on and state étale de Rham comparison. And so before I do that, I want to recall the analogy with singular cohomology. So recall for a smooth, proper C scheme Y of dimension D, we have an identification of singular cohomology of the C points, with Q coefficients tensoring up to C, with the de Rham cohomology tensored up to C, via Poincare duality, which will allow us to identify the left-hand side with homology, and the pairing, which is given by taking an integral of a form along a cycle. And so this is Hn de Rham, C over C times the complementary dimensional homology, YC C valued in C, where we just take a differential form and we take a cycle and we just evaluate it by integrating. And these numbers that you get out are often called periods. I think Elong mentioned this in the case of an elliptic curve this morning. And so that motivates why, in order to get the isomorphism, the comparison isomorphism, you had to tensor up to a bigger field, because the values of these periods are often highly transcendental, so you actually have to base change to C in order to get this identification. And so that's why we call things the Hodge tape period ring a period ring, because we have to tensor both sides by like B Hodge tape in order to get the isomorphism. So for a tall-Durand comparison, we need another period ring that hopefully will allow us to identify those two different cohomologies. So that's the next theorem, called p-adic Durand comparison. Also proved by faultings. So for X proper smooth A scheme greater than or equal to 0, there exists a canonical isomorphism of the Étale cohomology. That is base change to K, Kp, tensoring over Kp with B Durand, which I will say more about in a second, with Durand cohomology, Hn Durand of X over K, tensored also with B Durand. And this canonical isomorphism is compatible with the Galois action and filtrations. I should be getting a question at this point, because Durand cohomology does not usually have a filtration. It has a filtration coming from Hodge filtration, but it does not usually have a Galois action because it's defined over the base K. And on the other hand, Étale cohomology does not canonically have any filtration attached to it. So this doesn't really make sense until I tell you that B Durand is basically supposed to like fill in these gaps in what's missing on either side of the equation by having both a filtration and a Galois action on it. So B Durand was first constructed by Fontaine in 82. Where he constructed this ring and then also conjectured that such a relation would hold. So the Durand period ring B Durand has two properties. Namely, it has a filtration, which will be indexed by Z, such that the associated graded is B Hodge tape. And it should also have a Galois action, such that the fixed part of the Galois action is just K itself. And so these two properties will give the left-hand side of the theorem a filtration and gives the right-hand side of the theorem a Galois action.
Can I ask a question?
Yeah.
So here you mentioned this TPA equivariance of the map pi, and how is it used in the later argument?
You mean Galois equivariance?
No, not this round, but the earlier part when you define this map pi from A infinity to A0.
Oh, I see. It's just TP of A equivariant because this has the trivial action and this has like some action that like when you project to the first coordinate, it forgets, like it's invariant under the TP of A action.
Yeah, my question is like how is that equivariance was used in the later argument? Was it ever used in the later argument?
I think it was used to define this factorial map. Because I had to be able to say that this map was like TP of A equivariant, so that it won't do some homology. Yeah, but you also,
I see.
recalling back to this, I forgot to also mention the other set of eyeballs that I wanted to draw, which was that there are why did I base change to OC and not just to OK bar and do this whole proof? Because like this map could have been defined over OK bar. But the problem was this isomorphism only worked after taking p-adic completions, and OK bar is not complete. So I could only make that simplification after taking a p-adic completion, which is why I had to work over something that was algebraically closed and p-adically complete, which makes like C, working over C, the perfect candidate. Okay, so thanks. Great. Right. What I wanted to say about b-derom before we get into the construction is also to define this functor d-derom that I think Sasha will use later. So the definition of the functor d-derom from just finite dimensional C reps. I'm not sure if this is the right notation, but Galois representations of finite dimensional over with C coefficients to filtered K vector spaces is given by taking the representation V, tensoring it with b-derom.
So is it possibly Q representation? So we make it
I think usually when you start with the QP representation, you tensor it up to C and then you apply b-derom.
right, so b-derom kind of does the point with over C, with regular QP, so you really need to remember the QP structure for representation.
Oh, you're saying that I should start with a
Yeah.
QP representation.
Doesn't just apply to C.
Okay, thank you. So to start with the QP representation, we tensor it up with QP then. And then we then take the Galois fixed part. So this is how we define d-derom. And this ends up being a K vector space, but you have to check that. But after I introduce this notation, you can rephrase the theorem, this theorem, as just saying that d-derom of Hn tall x a bar Kp is just isomorphic to a derom homology. And this d-derom like form of this functor shows up a lot in p-adic Hodge theory, where you often like insert other period rooms. Okay, so these are isomorphic as filtered K vector spaces. Okay, so our last thing left is just to give you a construction of b-derom. I think I want to write over here. Now we're just constructing first b-derom plus, and we'll take the fraction field of b-derom plus to get b-derom. Okay, so I'll be using a lot this OC again, which recall is just OK bar completed. And the first thing I want to define is the tilt. OC, this is like a flat symbol, like a musical flat, but I'll call it OC tilt. Of OC is the inverse limit given by taking OC, inverse limit by x mapping to x to the p. So you really can think about this as being like an infinite sequence of elements of OC, such that x to the n plus 1 to the pth power just equals x to the n for all n. So this lives in product of OCs. But you can also show that this inverse limit construction is the same as taking the inverse limit of this OC modding out by P under the same x to the P map. And this is an isomorphism as rings, where the addition and multiplication on this inverse limit is just component-wise. Multiplication on this OC inverse limit is component-wise, but addition you have to define in some funny way as a limit. But from both of these considerations, you can observe that OC tilt is going to be a perfect characteristic P domain. The perfectness you can see by the perfect characteristic P part you can see by like this mod P like way to write it down, because it's characteristic P certainly, and it's perfect because the P's power map will be a bijection. And then from this OC inverse limit definition, you can see it's a domain. And it has a continuous GK action coming from the continuous GK action on each of the OCs. And the P's power maps are compatible with that Galois action. And also, yes, as a continuous Galois action. Okay. Then define the next step. So let me just keep a running summary actually of how we were constructing v-derom. So we had our OC, and so far we've built our OC tilt, and then we'll keep going. So the next step is to define A-inf. So A-inf is the ring of bit vectors of OC tilt, because we know that OC tilt is a perfect FP algebra, so we are able to take the bit vectors of it. And by the universal property of bit vectors, this will also have a Galois action because of the OC flat having a Galois action. And then we can define a theta map as a map which makes the following diagram commute. So A-inf is the bit vectors of OC tilt, and you can take that mod P just to get OC tilt. And OC tilt has a map to just OC mod P, which sends the sequence x0, x1, ... of elements to x0 mod P. So it's like projection onto the first coordinate and then mod P. And then we're going to define the theta map as being a map to OC such that this diagram commutes. And the way we're going to do that is by taking an arbitrary element in A-inf, which, because it's a bit vector of something, looks like taking some infinite sum of lifts, of multiplicative lifts of the elements in the base. So this is the multiplicative lift of xi's in OC tilt, which are non-zero. And then we'll send this element under theta to just, well, I guess it makes sense to send it to x0 times p to the I. And this xi0 lives in OC, the p to the I also live in OC, and this is an infinite sum where the valuation goes to infinity, so it converges and actually does give you an element of OC. And then you can check that this is a ring holomorphism, and you can check that it's Galois equivariant. Okay. So just to update our thing, we then define A-inf, right? And then that is the bit vectors. Are there any questions here? So now we want to extend this theta map by extension of scalars just to theta sub q. Now from AF, now we can invert P to OC inverting P. And this map by construction is surjective, and so this one will also be surjective. But OC, where you invert P, is literally just the field C. And it turns out that the kernel of this surjection is principal, and it's Galois stable. And then with a little bit of commutative algebra, we can define and claim some properties about B de Rham plus. So we get this plus the commutative algebra gives us that B de Rham plus is the kernel theta q adic completion of AF 1 over P. So this is just the classical I-adic completion for this ideal. And this, the part of the claim that I'm claiming is that this is a complete DVR with maximal ideal given by the kernel of theta. And it has a Galois action. So keep in mind that what we wanted out of B de Rham was that we would want something with a Galois action and we want something with a filtration. But very nicely, if you have a complete DVR with a maximal ideal, it is pretty easy to give this a filtration. This has an n-indexed filtration given by powers of the ideal, of the maximal ideal. And then, last step would just be, I can put it on the summary. So we then can define B de Rham as being the fraction field of this complete DVR, B de Rham plus. Which, since B de Rham plus had a filtration and Galois action, this will have a z-indexed filtration, and it will have a Galois action. And so just to recap the main steps of how we constructed B de Rham, we started with OC. We took the tilt. We took the Vic vectors of the perfect tilt. And then we defined this theta Q map after inverting P, which was surjective. And then we defined B de Rham plus as just the completion of AF 1 over P with respect to the kernel of this theta map. Yes, so now I've constructed B de Rham, so I think I'll stop here.
So, okay, no one has ever given me an answer when we haven't, so don't feel pressure to answer this question, but like, how would anyone come up with this?
Oh, I don't know. I guess, I don't know. Sasha, do you have any ideas?
I mean, there is an explanation for being he gave like 30 years after he came up with this. So this B de Rham plus, it's in a way the universal thickening of CD. So I mean, B de Rham plus, I was explaining, has a filtration. It's created pieces of J twist from CD. even what is that, or what else? Even what else, that is everything.
I think they don't call it a tilt, maybe, but it's. Yes.
I will say, I think I've seen a map of overflow like a post from Laurent Berger where he sort of gives a more analytic construction of BDR, which to me is more transparent and connected to the complex analysis now with this analogy.
Oh, whose post was it?
It's just a comment from Laurent Berger. He gave me a reference to some paper, but I found it more transparent. So I'll try to follow it. Other questions? Okay, let's thank Alice again.
Oh, I think you've like